Looking at the 5 most important problems in the Approximating Integrals section, the first problem I want to look at with you is just having us look at the function f of x is the square root of x. And what we're supposed to do with this is be able to approximate it on the integral, on the interval from x equals 3 to 5. And I'll approximate it using 4 rectangles, and I'm going to show every single rectangle formula, the L4, M4, and R4. I'll go ahead and start with the midpoint rectangle rule, M4. Now, if I were to draw out the square root function from 3 to 5, just to really try to show this as well as I can, I'm going to have a great disparity amongst the y values of the function. The square root function from 3 to 5 is relatively flat, but I can scale the y-axis however I want. So, for example, I could say it looks something like the following. I'm going to start at 3 and end at 5. Now obviously the y values at 3 are the square root of 3 and the y value at 5 is the square root of 5. I'm going to show quite a bit of difference in those values here just to try to make it easier to graph here. Okay, so here's my square root function from 3 to 5. I'm supposed to find the area under the curve. So if I use an M4 approximation, I'm going to have to separate this region up into 4 rectangles. The width of each of those rectangles is called delta x. Delta x by formula is always the end point 5 minus the beginning point 3 in this case, divided by the number of rectangles you need. Well, you need 4. So we have a width of 2 over 4 subdivisions. Each rectangle is going to have a width of 1/2. So I'll say, well, I need to split this up into 4 regions. That's 2 regions right there. And I'll say 3.5, and here's 4.5. Okay, so if I'm using the midpoint rule, M4, then the first rectangle is going to go from the value 3 to 3.5. But the height of that rectangle from 3 to 3.5, it's not determined by the height at 3 or by the height at 3.5. The midpoint formula says, well, for that very first rectangle, use the midpoint. Well, that would be whatever the height is at 3.25. So I would say, look at where f of 3.25 is, approximately right there, and then construct your first rectangle from x equals 3 to x equals 3.5. Sorry, that's not the neatest, but I think you get the idea. Now, the next rectangle would go between 3.5 and 4. The midpoint rule says the height of that rectangle is determined by the middle point of it. So in this case, 3.75. So again, remember the height of this first one I found by saying, well, whatever f of 3.25 is, and we'll find out that later. The height of this second rectangle between 3.5 and 4, it's going to be whatever the height is at 3.75. So I'll say I take that height, go over and down in both cases, and I know that that height was f of 3.75. For my third rectangle, again I would say, well, it's going between 4 and 4.5. The height of it's going to be deemed by 4.25. So the nice thing about the midpoint rectangle is it always overestimates part of each rectangular region and underestimates part. I'm trying to draw it in best I can there. That one's not too well drawn. This is f of 4.25. And finally, your last rectangle would go from 4.5 to 5. Its height would be determined by 4.75. So you say over and down. Now the point of what we're trying to do is that integration finds area under a curve. And integration is going to end up being an infinite summation. It's going to take each of these rectangles, make them infinitesimally thin, and take a sum of all of their areas. So we're just looking at an approximation right now of a finite number of rectangles to find out this region. Well, I would say my M4 approximation for the area under the curve, the square root of x from 3 to 5. So every single time we know area of a rectangle is length times width. Well, we already know all of these rectangles have a common width of 1/2. So I'll go ahead, factor out a 1/2. Now times the summation of the heights. The first height is going to be f of 3.25, then plus f of 3.75. I'll scroll over just a bit, plus f of 4.25 and plus f of 4.75. Now, we know that that would find the area of the entire region with the M4 approximation. Now, what are all these f of 3.25, f of 3.75? Like we discussed earlier, it's the height of the curve at that point. This curve is the square root function. So M4 is going to be 1/2 times the group. F of 3.25 is the square root of 3.25. Then I would say plus the square root of 3.75 plus the square root of 4.25 plus the square root of 4.75. It's just a matter of going to your calculator now and finding those values. Let's see here. We'll say 0.5, and I'll say times the group. We have the square root of 3.25, and then plus the square root of 3.75. Plus square root 4.25. Bear with me, this calculator is a little slow here on the computer. And finally we have our plus the square root of 4.75. And finally, that should find it. So I'm getting the M4 approximation, and whenever I get a decimal answer, I'll round to 3 decimal places and show that it's an approximation by putting the roughly equals to sign. M4 is roughly equal to 3.99. Now, without drawing a picture, let's talk about what the L4 and R4 approximation would be. It's going to be really easy. So I'll go back over here and say, well, okay, I drew out what the M4 approximation would look like because I used the midpoint of each rectangle to determine its height. So if I say, well, what's the L4 approximation? Hopefully you're thinking, well, that's easy. Each rectangle absolutely still is going to have a width of 1/2. So I'll say, okay, each rectangle has a width of 1/2. But now, the height of the first rectangle is not going to be using f of 3.25. It uses the left-hand endpoint of that first rectangle, f of 3. So we'd just say f of 3 plus f of the second rectangle between 3.5 and 4, f of 3.5. Then we would have f of 4. And for the last rectangle between 4.5 and 5, the height would be given by f of 4.5. You would never use f of 5 here because it's a right-hand endpoint of the last rectangle. We only use the left-hand sides. And now we know the L4 approximation is going to be equal to 1/2. When we plug all of these numbers into the function, it's just the square root of 3 plus the square root of 3.5 plus the square root of 4. Of course, we know that one's 2, plus the square root of 4.5. Now, I won't take the time to go to the calculator because it's just button punching, but when I did this earlier, the answer that I got was approximately equal to 3.862. So, not bad. Now, the R4 approximation. please once again look at the region that we have here. If I'm using the R4 approximation, I'll still have 4 rectangles. The height of each rectangle now is just determined by the right-hand endpoint of each rectangle though. So I'll still have that common width of 1/2, but the first rectangle, it is not determined, the height is not determined by f of 3, and it's not determined by f of 3.25. It's determined by the right-hand endpoint, f of 3.5. So I would say, okay, f of 3.5, then the second one's going to be f of 4, the third one, f of 4.5, and the last one that goes between 4.5 and 5, the right-hand endpoint, is given by f of 5. Please notice how the R4 and L4 approximation are pretty much the same thing, except R4 has all of the values of L4, except it takes away the first one, f of 3, and adds in the last one, f of 5. That will always be the case. Now, we know that the functional values of each of those just tell us to put the number inside the square root, since that's what the function did in this case. Square root of 3.5 plus the square root of 4 plus the square root of 4.5 and plus the square root of 5. When I did that earlier, I got the approximated answer of 4.114. Now, notice, since this is an increasing curve, the square root function increases as x increases, the right-hand endpoint, or sorry, the right-hand approximation, since it's using the right-hand endpoints in each case, will always be greater than, in this case, the midpoint, and the midpoint, of course, will be greater than the left-hand endpoints. For any increasing curve, the left-hand approximation is always going to give you the lower bound of your region, and the right-hand endpoint is always going to give you the upper bound of the true area of the region. The midpoint, you don't really know if it's an overestimate or an underestimate, but it's usually closer to the actual value. The L4 and R4 are kind of valuable because one is a lower bound. It's definitely lower than the true area, and the R4 is definitely an upper bound. It has to be greater than the true area under the region. So that's kind of interesting stuff. Let me move on to another problem here. All the problems in this section are great. It's kind of hard to narrow it down to 2, but I wanted to not spend forever on the video for you. If I look at the summation from I equals 1 to 30, gorgeous, and I have of the group 2i plus 1, but now we're squaring that group. Okay, so if I have 2i plus 1 quantity squared, well, if I'm going to put that inside of a summation, I need to algebraically expand out that group first. So I'll say this is I equals 1 to 30, 2i plus 1 squared. Any group squared, it's just going to be the first term squared. 2i squared is going to be 4i squared. And then whenever you square it out, it's going to be plus 2 times the first term times the second term. So that's going to be plus 4i. And then plus the second term squared, plus 1. Please don't be one of those students that thinks that a binomial squared is just the first term squared plus the second term squared. You always have that middle number, which is always just 2 times the first term times the second term. Always works out that way. Now, we'll use our summation formulas in the section. So what I need to use here, and these will be given on any test, I'll use that the summation of I squareds from I equals 1 to n, and I'll refrain from putting the indices. Remember, it's implied to be 1 to n if you don't put it. It's equal to n times n plus 1 times 2n plus 1 all over 6, and that the summation from I equals 1 to n of I is n times n plus 1 over 2. The only other thing that we need here is just understanding that the summation of 1's from 1 to n, remember that means 1 plus 1 plus 1 plus 1 plus 1 n times. Well, of course, that's just going to be n. Okay, this works for all three of those now. So I'll go ahead and separate this out and say, okay, so if I have this summation, I'll go back to the original problem. Summation from I equals 1 to 30 of 2i squared plus 1 quantity squared. It is equal to, I'm going to break it into three separate summations. This summation can distribute to each of these three terms here. So the first term, it's the summation from 1 to 30 of 4i squared. I'll factor a 4 out of that, then say times the summation from I equals 1 to 30 of I squared. Plus, I have the summation of 4 i's. Once again, I can factor a 4 out of that individual summation and say I equals 1 to 30 of I. And then lastly, I would have plus the sum from I equals 1 to 30 of 1. Now, in each of these, the n value that we have in our general formula is what we have on top. These general formulas are for I, the summation from I equals 1 to any number of n. So n just gets replaced with 30 in this problem. So this entire summation is going to be 4 times the group. I have 30 times 31 times 61 for the first one. All of that's over 6. And then for the second one, I'll have plus 4 times the group, 30 times 31. And that's going to be divided by 2. And then the last one, it's the sum of 1's from 1 to 30, so that's 1 plus 1 plus 1 30 times. We know that'll just be plus 30. Okay, so now this should give us the correct answer. Again, it's kind of slow using this calculator, so I won't do that. But when I did this earlier, I got an answer of 39,710. Okay, let me show you the shortcut way to do this on the calculator. This is the way that we would do it by hand and find the summations by hand, but your calculator does have a built-in summation that'll be a little quicker than typing all of that in. It's math, and it'll probably be quicker if you arrow up. Notice 0, math 0, automatically brings up the summation. Now, just for ease, I'm going to use the variable x in this problem. I'll say it's the summation from x equals 1, and I'll arrow up to 30. And then I'll go to the summation box, and I need to say it's of the group 2x plus 1. I'll close the group, and then I'll square it. This should work perfectly. It better match that answer of 39,710. Gorgeousness. So you can do it out by hand using the formulas. Well, actually preferable. I would require to see this work on a test, but we do have the shortcut feature on the calculator to help out with that as well. Let me look at another problem similar to this, yet a little different. The last one we had indices that started at 1. Those used the formulas directly. Hypothetically, what if our index does not start at 1? So something like, if I say find the summation from I equals 26 to 58, of I squared. So this would be asking you, what is 26 squared plus 27 squared plus 28 squared all the way up to 58 squared? That'd be time consuming if you did it that way. Well, fortunately we have formulas to help out, but those formulas for summations that we have start at 1. So we can say, well, all we have to do is break this up into two separate summations. It's the sum of all numbers from 1 to 58 of I squared, but we know that that will be too much. We need to subtract off the summation from I equals 1 all the way to the last number that we don't want, which is 25. So then this should enable me to put these into my formula without any trouble whatsoever. The summation for the I squareds, again, recall, and this will be given, the summation for I squared in general is equal to n times n plus 1 times 2n plus 1 all over 6. So for this problem, our first summation, I'll go back to the original problem. The sum from I equals 26 to 58 of I squared is equal to, well, the first sum. I know that that's just going to be this summation formula with a 58 plugged in for n. So I'll have 58 times 59 times 2 times 58, which is 116 plus 1, 117, all over 6, minus the sum from I equals 1 to 25 of I squared. Well, okay, that now n is equal to 25, so we'll say 25 times 26 times 2 times 25 plus 1, 51, all over 6. So if we do this out by hand, we'll get our 58 times 59 times 117. We're dividing that first fraction by 6, and so we'll get that this summation is equal to 66,729. Of course, we need to subtract the second quotient. We'll get 25 times 26 times 51, and we're dividing that by 6. 5525. So when we take our 66,729 minus the 5525, we're getting our 61,204. Just to check real quick, that better match with the summation shortcut on the calculator. Some math sum 0, you could arrow to it, or I'll just hit math 0. I'll say this is the sum from x equals 26 up to 58 of x squared, and should match. And it does. Okay, so now the more interesting problems in this section, at least in my mind, are these that ask us to find an infinite summation of rectangles under the curve to estimate the area. Well, actually, to give the exact area. Some of the easier ones give us a curve which we could find geometrically as well, but they still are good problems because they get the point of the infinite summations with the Riemann sums. Now, I will always use right-hand rectangle estimation formulas for this, and that's the same thing I would ask on a test. As you put infinitely many rectangles under the curve, it is completely irrelevant whether you use left-hand rectangles, midpoint rectangles, or right-hand rectangles. So I say, why not just do the one with the simplest formula? And that happens to be the right-hand rectangle formula. So I'll say, well, okay, let's say we're looking at f of x equals 4x minus 2 from x equals 1 to 3. Okay, so I'm going to be using the right-hand rectangle formula with infinitely many rectangles under the curve. Please remember this x equals 1 to 3, that's your x equals beginning point to ending point, A to B. So in this problem, A is 1, B is 3. Remember, delta x, your general formula for it is ending point minus beginning point divided by the number of subintervals, which in this problem is n. So we can see that the width of each rectangle is going to be 3 minus 1 over n, or 2 over n. Okay, so my general formula here is r sub n is equal to the limit as n approaches infinity. Your book tends to use capital N's. Most people would use lowercase n's. Doesn't matter though. And these summations are always going to be from I equals 1 to n. It's implied that it's I equals 1 to n if you do not put indices on it. So I'm going to refrain from indices just to save a little bit of time. I have the summation from 1 to n of f of a, so that's finding the height at the very first endpoint, but since it's the right-hand rectangle rule, I need to say plus I delta x. I need to add in the width of that first rectangle to get to my first height. And then times the width of each rectangle, well, the width is going to be the delta x. We'll plug in 2 over n for that in the next step. So r sub n is going to be the limit as n approaches infinity of this summation. We already said f of a in this case is 1. So we'll have 1 plus delta x is 2 over n. So that when you multiply by I is going to be 2i over n times delta x, 2 over n. I'll say that this is equal to the limit as n approaches infinity. 2 over n can be brought out in front of your summation. It doesn't have the indices in it. Now that f of 1 plus 2i over n, we already know what that is. The function f is 4x minus 2. So all I have to do is say, well, then this summation is going to be 4 times the group 1 plus 2i over n. The 1 plus 2i over n takes the place of x in your function, and then you were subtracting 2 there, so I still have to subtract 2. Now from this step to the next, the only thing I'm going to do is distribute that 4 through that group and simplify, subtract the 2. I'll bring this down here and say, okay, this is going to give me the limit as n approaches infinity of the summation. I'll have, please notice, 4 minus 2, I'll just have a constant of 2 in there. But then I'll have plus 8i over n, the 4 times 2i over n. Now, as soon as I do this, notice what I forgot here in this step, guys. The 2 over n has to be kept out in front. So I'll say I have this 2 over n times the summation of 2 plus 8i over n. I'll break this up into 2 individual summations and say, okay, this is the limit as n approaches infinity, and I'll have 2 over n times the summation of 2's, I'll say for now. And this limit as n approaches infinity applies to everything after it in the expression. Some people put the limit with each and every term, and I do that sometimes. It's not a mandatory step, though. It's implied to go everything in the expression after it. Now I'll have plus 2 over n does need to be brought in front of each summation of 8i over n. My next step, I'm going to factor the 8 over n out of this one. I'm going to go ahead and say that the summation of 2's is just 2 times n, because remember, this is the summation from I equals 1 to n, so that means you're going to keep on adding 2 to itself n times as n approaches infinity. R sub n is going to equal the limit as n approaches infinity. My first term is going to be 2 over n times the summation of 2's, which is 2n, plus 2 over n. And then the second one, anything that's not in I can and should be factored out. I factor out the 8 over n, but then I'm left with the summation of i's. Well, fortunately, we have a formula that tells us what the summation of i's are equal to. Now, this first one doesn't need the limit as n approaches infinity anymore, because the n just cancels out of it anyway. I'll say I'm going to have 4 plus, the second one does still need a limit as n approaches infinity, and I'll have 16 over n squared. The summation of the i's is equal to n times n plus 1 over 2. Okay, so now I have 4 plus this limit as n approaches infinity. Whenever you have a limit approaching infinity, if you can see that the degree of the numerator and denominator is the same, then your answer is just always going to be at the fraction of the leading coefficients. So here I can see that I have the limit as n approaches infinity. I could go ahead and reduce down the 2 and the 16 and say, well, my denominator is just going to have an n squared. My numerator, the largest powered term of n would also be an n squared up there, and once that 2 cancels with the 16, its coefficient would just be an 8n squared. Now, I know that there's also going to be a term of n, but just to show that it's irrelevant, I don't care that there's any other terms up there. If it doesn't matter, you can say 8n squared plus ... The rest is irrelevant. So now, when I take this limit as n approaches infinity, by rule, anytime the degree of the numerator and denominator is the same, you can just take the fractional leading coefficients for your answer. So when we take that limit, we get 4 plus 8. We know that that answer is 12. Ooh, that's a ugly 12 circled. Now, you say, well, okay, that was a very cool way of finding the answer. Yes, it was. But there is another way in these simpler problems. This one could have also been done graphically. So just to check this answer graphically, the function was 4x minus 2, and we were looking at it from 1 to 3. So if I'm looking at f of x equals 4x minus 2, well, all I need to do is, well, what's f of 1? We know f of 1 is going to be 4 times 1 minus 2. It's going to be 2. f of 3 would be 12 minus 2 is 10. So I'll plot these points. I have the point ordered pair 1, 2, and the ordered pair 3, 10. I'll put up here. Connect the dots. Make a big dot to connect. And now I'm trying to find the area under this curve. So I could split this area up into 2 very easy to find regions, a triangle and a rectangle. I'll call this area 1, I'll call this area 2. Now, the reason that we're doing this here in the beginning is that integration is an infinite summation. So the end goal of what we're really trying to get to is the integral starting at 1 and ending at 3 of the function 4x minus 2 dx. This literally means, the reason this looks like an S is it means sum all of the infinitesimally small areas with a height of 4x minus 2, and each rectangle has a width in an infinitesimally small change of x. You're going to sum those rectangles starting at 1 and ending at 3. That is literally what this integration in this problem means. Well, instead of doing that, we found an infinite sum using a Riemann sum up here, so we got our answer of 12. Another way, without attacking the definite integral with integration, is to use these areas. So I'll say, well, this is equal to my area 1 plus area 2. Area 1 is a triangle which has a formula 1/2 base times height. So I'll say 1/2. Well, the base goes from 1 to 3. It has a length of 2. And the height, now be careful here, it does not have a height of 10. We know it has a height of 10 minus 2, has a height of 8. And then plus the area of the rectangle below has a width of 2 and a height of 2. So notice, just like my Riemann sum where I ended up with 4 plus 8, same thing I'm getting here. The area of the rectangle is 4, the area of the triangle above is my 8. I have 8 plus 4 again for a total area of 12. Gorgeous problem. Love that. Okay, One last problem here, and if you're good with this one, you should be in fantastic shape. I want to do another Riemann sum, but with this one, it's quite a bit more challenging than the last. It's one that we could not do geometrically. We have f of x equals x squared plus 7x. And guys, I want us to find the area under the curve between 6 and 11. So the area between the curve and the x-axis starting at 6, ending at 11. We're going to do that with an infinite Riemann sum using the right-hand rectangles. Limit as n approaches infinity of the summation. And again, anytime I do that, it's implied to be from 1 to n. We'll look at f of a plus I delta x times delta x. Now again, let's make sense out of that. Well, we'll say this is the limit as n approaches infinity of the sum. F of a, what is a? It's your starting point. F of 6 plus I delta x. Please remember, delta x is just the width of each rectangle. That's always going to be the distance of your region divided by the number of rectangles. In this case, it's 5 over n. So delta x times I is going to be 5i over n. And then times delta x times 5 over n. Every time the first thing I do, just like in our finite case, where we always factored out, notice if I scroll up here, the very first thing I did in these finite cases was I factored out the 1/2, factored out the width in the very beginning times the summation of the heights. That's the same thing you do in this infinite sum problem. You factor out the common width times the summation of the heights formula. So I'll say R sub n is equal to the limit as n approaches infinity, 5 over n, and now I'll say times the summation of heights. Well, I have f of 6 plus 5i over n. What is that in this problem? It's going to be the summation of, this has to take the place of x in your function. So I'll say the group 6 plus 5i over n, quantity squared, plus 7 times the group 6 plus 5i over n. All of that goes inside of our summation. Okay, now I can say this is going to be the limit as n approaches infinity, 5 over n. I just need to do some algebra now on the inside. Ooh, that's an ugly summation. Sorry, guys. When I say, well, what is the group 6 plus 5i over n squared? Any binomial squared is the square of the first term, 36, plus 2 times the first term times the second term. 2 times 6 is 12, times 5i over n is going to be 60i over n, plus the last term squared, that'll give me 25i squared over n squared. Distribute the 7 into the second group and you'll get plus 42 and plus 35i over n. Now, this is going to yield, the limit as n approaches infinity, 5 over n. I need to simplify like terms inside that summation. The constants, I'll have 36 plus 42, that's going to be 78. I knew there was an 8 in there somewhere. And then I'll have 60i plus 25i. I think that's 85i. Ooh, sorry. I almost made a horrible mistake. The second term, 5i over n quantity squared, is 25i squared over n squared. Whew. Okay, so mistakes are okay as long as you catch them. But now, the like term is the 60i over n and the 35i over n. That'll be 95i over n. And then I'll have plus 25i squared over n squared. There's no common term with it. Beautiful. Okay, now I'm going to break this up into 3 separate summations, and then we're going to find the sum of each one individually. It'll be no problem. We'll have the limit as n approaches infinity, 5 over n. Now, times the summation of 78s. We really already know that that's going to give us 78n. This means 78 plus 78 plus 78n times. That's just going to be 5 over n times 78n. Then I'll have plus 5 over n. And in this second summation, I'm going to go ahead and I know it would be the summation of 95i over n, but anything that's not an I can and should be factored out. I'm going to go ahead and factor that out in this step and say I'll have 5 over n times 95 over n, and then I'll be left with, in that second summation, the summation of i's. In the third summation, I'm going to do the same thing. I'm going to factor the 25 over n squared out. 25 times 5 is 125. I'll have n cubed in the denominator. And then I'll have times the summation of I squareds. Those, in order to simplify, we have to use our sum formulas. Okay, we'll have this limit as n approaches infinity. My first one, 5 over n times 78n. Plus my second one, that 5 over n was distributed to it as well. Here I should have said 5 times 95. 5 times 95 is 475. I'll go ahead and put that in here, guys. So, that's an ugly 475. Take my word, that's 475. Over n squared. And then times the summation of i's. Well, the summation of i's formula is n times n plus 1 all over 2. And then for my last one here, we'll have plus our 125 over n cubed. And it's multiplied by the summation formula for I squareds, which is n times n plus 1 times 2n plus 1 all over 6. Now, when I go back over here and say this r sub n is going to equal the limit as n approaches infinity. The first term actually doesn't even need the limit as n approaches infinity because the n's just completely cancel out in it. And you're left with 5 times 78, and the 5 times 78 is 390. We have 390 plus, the second one is, again, inside of a limit as n approaches infinity. Your numerator is going to be 475 n squared, and again, I only care about the coefficient of the leading term in the numerator and the power of that numerator. And then the denominator is going to be a 2n squared. For my next term, please do remember part of it's off the screen, so there it is. I can see if I multiplied out every single term in the numerator, the greatest power of n would be an n cubed. Its coefficient would be 2n cubed times 125. It would be a 250 n cubed. Yes, there's other terms of n in the numerator, but they are irrelevant. Your denominator is 6n cubed. So now, when we take a limit as n approaches infinity, anytime the degree of any fraction in the numerator and denominator is the same, the limit is just the fraction of the leading coefficients. First term didn't need the limit, the n's canceled. The second one now, when we take the limit, it's 475 over 2. And our third one, we get plus 250 over 6. Of course, that would reduce down to at least 125 over 3. I'll leave it 250 over 6 here. Now, when we add these three together, we'll get a 669.16 repeating, or 1/6. I'll just say 1/6 repeating for our final gorgeous answer. Hopefully you enjoy these problems as much as I do. We'll talk again next section.